Hey, hello, Marauders. Can you find me in the crowd? It's like, where's Waldo? And this is our last week, so please read the announcement I announced. It says this is June, so there's lots of helpful information there. But this week, I'll tell you a little bit about calculus. You don't have to turn anything in. Just watch the videos for this week, learn a little bit, because calculus is really abstract and bizarre and kind of crazy and pretty advanced, but at least you'll get a few little hints of what's going on. And here's my little rabbit to cheer us on. Whee! So let's learn some calculus. I only know how to multiply. All right, so we'll learn a little bit about calculus. Just give you some previews here, because you're going to do a whole chapter on something called limits, which is kind of thing. What is a limit? You need to know your limits. So we're looking at a little bit of the book right here. And they give you a little thing to read here. Motion and change are the very essence of life. It says the tools of algebra and trigonometry are essentially static. Numbers, points, lines, equations, functions, and graphs do not incorporate motion. The development of calculus in the middle of the 17th century provided a way to use these static tools to analyze motion and change. It took nearly 2,000 years of effort for humankind to achieve this feat, made possible by a revolutionary concept called limits. The invention of limits marked a turning point in human history, having as dramatic an impact on our lives as the invention of the wheel and the printing press. In this section, we introduce this bold and dramatic style of thinking about mathematics. So we're exiting the world of algebra and entering the world of calculus. Okay, so kind of weird. Here's these two people walking on a line. It says, here's the equation, x squared minus 4 over x minus 2. And actually, it's a straight line. You might say, well, why isn't it a parabola? I see x squared. Well, the reason is you got to have your algebra skills down. You got to be able to factor. Okay, the bottom's x minus 2, but could you factor the top, x squared minus 4? Isn't that a perfect square? Positive 2 times negative 2. Okay, so I factored it. Why? Because now it's a multiply, and you could cancel. So this equation is really just the same thing as x plus 2. And I know we say f of x, but isn't f of x the same thing as y? So isn't this the line x plus 2? Oh yeah, the y-intercept is 2. Remember, like y equals mx plus b? So it starts at 2, and the slope is up 1 over 1, up 1 over 1, up 1 over 1. So it's really the same as x plus 2. However, there's a hole in the graph, because if I said, what is it when you plug in 2? You can't plug in 2, because in the original problem, 2 minus 2, that's 0. And you can't divide by 0. So this looks like a straight line, but there's a hole in it. But that's where calculus comes in, the idea of limits. We found a hack. Like, how could you divide by 0? But we're not there yet. Okay, but you can't plug in 2. But you can plug in numbers really, really close to 2. I'm going to turn the page. So here they said, let's plug in 1.99. And you could use a calculator. And they plugged in 1.99. And over here they did like on a calculator. And they said, well, I got like 3.99. Okay. Then they plugged even closer. 1.999. They got 3.9999. And they got 1.99999. And they got 3.99. In fact, the closer and closer you get to plugging in 2, what are you getting close to? Well, that's getting close to 4, isn't it? Now, you can't plug in 2 because 2 is an error. But you can plug in 1.99. So you can't plug in 2 because you can't divide by 0. But we could divide by, you could put this in, because that would make this almost 0. Would it make it like it would make the bottom kind of like 0.0000, however many zeros you want, and a 1. You could divide by that. It's kind of like that. I'm not touching you. I'm not touching you. I'm not touching you. So you're really, really close. So what that's saying, and then they tried it from, well, before we get that, looking at this graph, if you pick the number really, really close to 2, the answers get really, really close to 4, don't they? But like if you're almost at 2, you're really at 3.99, but you're almost at 4. Likewise, if we did it from the other direction, 2.01, you're going backwards, 2.01 makes the answer a little bit bigger than 4. But as you get closer to 2, the answer gets closer to actually being 4. So we try to say the graph is approaching it. And we have this neat way of writing this. Okay, so here's how we're going to write it. We're going to write something called lim, which is short for limit. And we're going to say as x, and this means approaches, as you get close to 2 from the negative side. Now I put a little minus here. I didn't put it in the wrong spot. I don't want negative 2. This means 2 and then go a little bit smaller than 2, 1.99. Of this problem, f of x, the answer, so when you put a number really close to 2, but this means approaching from the left, a little smaller, a little on the negative side of 2, your answer is getting close to what? It's getting close to 4. You're approaching 4. You can't actually plug in 2. Likewise, over here, if I picked a number a little bigger than 2, so I would say if you were getting really close to 2, but I picked a number 2 plus, this plus here means a number a little more than 2, like 2 and add a little bit, 2 and take off a little bit. Sometimes they say from the right. And when you put it in the rule, you could write the rule, you're getting 4 again. So when you put a number really, really close to 2, you're getting something really close to 4. So this just means, hey, if you plugged in a number close to 2, you're going to get an answer close to 4. And since these are the same answer, you could actually just combine them and say, as x approaches 2. If you don't take a little plus or minus on this thing, people just say, well, it doesn't matter. Anywhere you come from, anywhere, right side, left side, you're getting close to 4. Okay, so we're saying you get close to 4. However, if I said, oh, so by the way, what do you get if you plug in 2? That would mean, what do you get if you actually plug in 2? Now remember, when I plug in 1.999, you get close to 4. You got like 3.999. And when you pick it a little bit bigger, you got to answer a little bit bigger than 4. Something like that. I might have an extra 0 there. But if you actually plugged in 2, what do you get? Wait, you can't plug in 2. You get an error. So f of 2 is an error or undefined. But if you put a number really close to 2, you could get 4. Okay? They do write it down here. This says, as x approaches a, so some number you're thinking about, 5, and whatever the rule is, and this is what you're getting. Here's another one. Sure, can you see what this says? As you get close to 4, what answer do you get? So you're not supposed to plug in 4, but plug in something really close. So down here they said, well, let's plug in 3.99. So down here they plugged in 3.99, and they got 47.76. I guess you have to, get a calculator out, but you could say, okay, 3 times 3.99 squared. So they plug that in. So they go, see, we got to do the exponent first, times it by 3. Now this is almost 4, isn't it? If you put in 4 squared would be 16, and 3 times 16 would be 48, wouldn't it? But we had to pick a little bit bigger, a little smaller. So they got 47. And when you got closer, got a little bigger, when you got even closer to 4, you got even closer. You're almost to 48, aren't you? So once again, they're going to say, you're getting close to 48. What about if you pick bigger than 4? As you get really close, like 001, the answer is close to 48, but it's a little bit bigger. See how you're getting closer? So we could just say the limit as you get close to 4. They didn't put a plus or a minus on this. We just say you're going to get close to 48. Okay, check out this one. It looks like a little roller coaster ride. Like, so you're riding on the roller coaster. Whee! But there's a hole in the track, and there's a hole here. And here's the question. As you get close to 4 is x. They always put x here. When you pick a number close to 4, what do you get? I don't see an equation, but I'll just look at this graph. When you get close to 4, what are you getting close to? So when I'm like, you're getting closer and closer and closer to 4, I'm getting close. When I get closer to 4, this graph is going uphill, uphill, uphill. It's like there's a little guy here, right? He's going up, up, up. How high is he climbing to? He's getting close to 7, isn't he? So we could say we're getting close to 7. So Rosie, get close to 7, but as we get close to 4, from the negative side, number's a little less. What if we picked a number getting close to 4, but a little bit bigger. A little bit bigger than 4 of some rule. Is it also 7? Let's try it. As we come from this side, as I'm getting closer to 4, the graph, I'm going up, and I'm going, I'm also getting close to 7. Well, duh, right? So you could actually just say, put equals 7. If you don't see the plus or minus, it means from both directions. But if somebody says, oh, by the way, what is f of 4? Where is the dot at 4? Remember, there's also a guy coming from this direction. They also, it's like two explorers are looking for treasure. I'm hiking up the mountain looking for the treasure. There's a hole in the ground. Someone stole my treasure. It's supposed to be right here at 7. As I'm marching off to 4, the treasure is supposed to be at 7. This guy says, I came from the other direction. I was heading to 4 also. And I expected to find the treasure at 7, but somebody dug it out of the hole. They picked it up and dropped it down here. So someone's going to say, so actually, if you were actually at 4, where is the treasure? The treasure is actually right there. The treasure is actually at 2. Okay, so it could actually be a different answer. Sometimes somebody puts the dot right there and says the treasure is there. Okay, so how do you do some of these problems of another graph? Here's the shortcut. Here this says, what if you plugged in a number really, really close to 5? What do you get? You know what you should really do? Just plug in 5. Of course, you could plug in something smaller and plug in something bigger, but I don't see anything funny happening here. Just plug in 5. I bet you the answer is 7. But sometimes you can get a weird one. Oh, that's like, oh, I can't actually plug in 0. Darn, I got to plug in something close to 0. Okay, so here's the answer to your question. Someone gives you an equation like this. Remember, that's the one we originally started with and says, what is it when you approach 2? And you're like, darn it, do I got to plug in 1.99? No, just plug in 2. Oh, I can't plug in 2. I get 0. Darn, I got to plug in 1.99. No, you have to use your tricks. Like I said on this one, here's what you can do as a shortcut. If you don't really, really want to do a bunch of work and plug in decimals, factor the top and kind of go, hey, you know, this would cancel out. I'm left with x plus 2. So this equation is kind of like x plus 2. Why don't you just plug 2 into this thing? What's 2 plus 2? 4. That is, whoops, I'll go back here. That is your answer. I bet you it approaches 4. I bet you I'm right. I didn't plug in 1.99. Sometimes you can say I'm supposed to plug in something close, but just plug it in anyway. But I can't. Well, what if you manipulate it a little bit? Then I could plug it in. And you might remember, that is the answer, isn't it? Even though there's not a dot at 2, but if you did that little manipulation and plugged in 2, it actually is approaching 4. We're both approaching 4. Let's try one where the explorers are going to different places. Okay, check out this graph. Let me cover up part of it. Here's an explorer coming from this side. He's like, I'm going to go find the treasure. He's following this curve, which happens to be x squared plus 1. And everybody that's using a number smaller than 1, like a negative number, is following this line. As he approaches 1, from the negative side of the graph paper, in other words, from negative numbers, kind of. What number is he headed towards? Let's follow him. Where is he thinks the treasure is going to be? When he gets close to 1, that's positive 1, he's getting close to right there. He's getting close to, what is the height? Don't say 1. We know he's going to x is 1. But this, you're always putting, remember, you're always putting a y answer here. You're always putting a y answer here. He's getting close to 2. He thinks the treasure is at a height of 2. But what about a guy coming from the other direction? Look at this guy. It says if you're coming from a number bigger than 1, if you try a number bigger than or equal to 1, remember piecewise functions, he's supposed to follow this line. So he's exploring, says, I got a treasure map, and I'm headed 4, 3, 2, coming down, 1. As x gets approached to 1, as x approaches 1 from the positive side or from the right side of the paper, he's headed to this dot, which is at a height of 4. We got 2 different answers. He thinks the treasure's at 2 because that's the height he ends up at. He ends up at 2, the red guy. But the blue guy, he's getting close to the same number, 1. We're both headed to 1. He ends up at 4. We have 2 answers. Thus, we say the limit does not exist. For it to exist, they have to both go to the same place. Who's going to find the treasure? This guy. If I actually said, so where is the actual treasure? If you could actually just teleport your way to f of 1, if you could actually teleport to, oh, that's a hole. There it is. The treasure is actually at 4, isn't it? But this guy headed to 2 and he headed to 4. That's the idea of limits. That's how close you can get. So in calculus, you'll deal with various funny graphs, and they'll have questions like, okay, as you approach 2, x is 2, from the negative side, where are you going? So I like to cover up my graph. I'm approaching from the negative side of the paper, and just see where do I get? I'm approaching 1, 2, I'm at 4. I would just say the answer is 4. But if you approach 2 from the other side, x is going to 2, x, 4, 3, 2. Okay, where am I at? Look at the height, 2. Oh, this answer is 2. Do they agree? No, we have different answers. Sometimes you don't get to see a graph. Sometimes you only get a rule, and you got to figure out, this one says, do you think there's a hole in the graph? So you got to try it from each side. There's more to it to learn. And here's the last thing. Here's a kind of a crazy looking graph. Sometimes they say, if I said as x approaches 100, you go, where's the graph approaching? You go, let's see, well, what is that? You look over here and go, whatever this is, maybe it's 50. You'd say, well, the graph seems to be approaching 50. And sometimes they'll say, okay, how about this? What if I said, what is the limit of something? Let's pick the number infinity. What if I said, as you head to infinity, as your explorer goes and goes and goes off the paper, as he says, my map says to walk for the rest of my life to infinity and beyond. What height does he end up at? Well, this says just go up, 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 up. I guess he's just going to go up, 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 up. What height is this? How high up is he? He's in the clouds, isn't he? There's the clouds. He's at a height of infinity, okay? He could be going infinity. And sometimes you'll have a graph like this. As this guy heads off to infinity and beyond, as he heads to infinity, is he going up into the clouds? No, he looks like he's getting closer and closer, maybe, to an asymptote. He might be actually headed to 0. He's getting closer and closer to the ground. He's actually just going to end up practically touching the ground, but he's not quite touching the ground. He's like a magician. He's hovering just barely above the ground. Okay, that's the end of today's lesson. Remember, there's nothing to submit and turn in. Tomorrow, I'll tell you about how to use this information to find the slope of a curved line, like a parabola.